Hi students, in this video we're going to go over section 411, other proofs involving sets. So I know we did already a section that went over proofs involving sets and we did the element method of proof. In this section our goal is to discuss some additional proofs involving sets, including the element method but for defined sets, counterexamples, method of exhaustion, and proof by contradiction. So the first example covers how to complete a proof using that element method and a counterexample, but for when sets A, B, and C are defined. So for example 1, we have defined sets for A, B, and C. So A is the set of all elements X, which is in the set of integers, such that X is equal to 6A plus 4 for some integer A. Set B is the set of all elements Y, which are in the set of integers, so Y is an integer, such that Y is equal to 18B minus 2 for some integer B. And set C is equal to the set of all elements Z in the set of integers, such that Z is equal to 18C plus 16 for some integer C. So for part A, we're going to prove that B is a subset of A. So we're going to start with proof. This is part A. We're going to start with proof, and we are going to suppose that Y is an element of set B. So remember, to show that B is a subset of A, you start with an element that's in B, and you show, hey, it's also in set A. So suppose that Y is an element of set B. By definition of B, Y is going to equal, just going to copy this part down, Y is equal to 18B minus 2, and this is for some integer B, and we're going to let, okay, here's where we're going to end up doing some scratch work. Let's copy this part down too. So I'm going to do scratch work over here in this margin. This is not a part of the proof, it's just so I can work out some of the algebra. And generally, I already start the proof, but generally the scratch work would be done before the proof. So Y is going to be equal to, I'm going to actually copy this part down. The X is equal to 6A plus 4. So I'm going to copy this part down, the 6A plus 4. 6A plus 4. Now I know this is for the X, but I'm picking a Y and I want to show that Y is in A. So if Y is in A, Y has to be equal to the 6A plus 4 also. So I'm just going to do the scratch work on the side. So I have that Y is equal to 6A plus 4, and then Y is 18B minus 2. That is the definition for the Y. Just using this here. Keep the right-hand side as it is, and then we're going to solve for the A. You already have your B. B is fine. It's taken care of within the proof. You're going to solve for the A. So when we do that, we have 18B minus 6 equals 6A. And I'm just going to divide both sides by 6. So I'm going to get that A is equal to 3B minus 1. So you solve it for A. So then you go back to your proof on the left, and we're going to let A be equal to 3B minus 1. So B is some integer, and A is going to also be an integer, but it's going to be an integer of the form 3B minus 1. I'm going to say then A is an integer, and this is because B is an integer and your sum and product of integers is itself an integer. And I'm going to take the X. X was the 6A plus 4, so I'm going to just take that, and I'm going to replace the A with what it's equal to, the 3b minus 1. You still have your plus 4. And then I'm going to get 18b minus 6 plus 4. This is 18b minus 2, which is equal to y. Thus, by definition of set A, y is an element of A. So you show that you started with y being in the set of B because it's of this form here, 18b minus 2. And then you picked a value, some integer a that's of this form, 3b minus 1. And then what you did, you used this part here, which is your definition for set A. And you show that when you replace the A with what it was equal to in terms of B, 3b minus 1, and you simplified, you just got back the value y, which was an element in B. But we started with 6a plus 4, which was the definition for an element in set A. And we should end with a little QED or a little box or something to let the reader know that the proof is over. Now we're going to do part B. We're going to prove that B and C, these two sets here, are actually equal to each other. So if it's equal to each other, then we're going to, this is one of those two-part proofs for the element method. You have to show that B is a subset of C and that C is a subset of B. Got to show both those things. So you're going to start with proof. And we're going to do part 1. And part 1 will be proof that B is a subset of C. So we're going to suppose Y is an element of B. And we're going to show through algebra and so forth that, hey, it's also in C. By definition of B, Y would have to be equal to 18b minus 2. And this is going to be for some integer B. And then we're going to let C be equal to something in terms of B. Picking C because of set C. And I need some scratch work. So I'm just going to do scratch work over here. Just going to make a look at a note. So Y is equal to 18. I'm actually going to make Y equal to the Z part. So 18C plus 6. And then Y is the 18B minus 2. And then we're going to solve this for C. So we have 18C is equal to 18B minus 18. So C is equal to B minus 1. I'm going to go back to my proof. That was just a scratch work. So I'm going to let C be equal to B minus 1 based on that scratch work. And I'm going to say then C is an integer. Because it's the difference of integers, so it would have to be an integer. And 18C plus 16. That's the definition for set C, is equal to 18b minus 1, replace the C with b minus 1, plus 16, 18b minus 18 plus 16, 18b minus 2, which is equal to y, right? What we have up there. Thus, y is an element in C, because we started out here with your definition of C. So I'll say by definition of C. Now we're going to do part 2. So for part 2, this is the proof that C is a subset of B. So I'm going to say suppose Z is in C, and then by definition of set C, Z would be equal to 18C plus 16, this part here, for some integer C. And we're going to let B now be equal to something. Let's go back to our scratch work. Just going to solve this here for the B. So I'm using my same scratch work basically. So B is going to be C plus 1. So let B be equal to C plus 1. Then B is an integer, right? Because it's the sum of integers. And now we're going to use the definition. Oops, that should be a negative. We're using the definition here for set B. So fix this, that should be a negative there. And this is going to be equal to 18 times C plus 1, replace the B with C plus 1, minus 2, which is 18C plus 18 minus 2, which is 18C plus 16, which is equal to Z, right? Because you have that up there. Thus, Z is an element of B. By definition of set B or of B. So since B is a subset of C and C is a subset of B, then B is equal to C. QED. Now part C, we're going to disprove that A is a subset of B. So to disprove it, we're going to use a counterexample. So we'll write counterexample. And we're going to show that A is not a subset of B, we're going to find an element in A that is not in B. All right, so the elements in A have to be of this form, 6A plus 4. Four is an element of A. The number 4 is an element of A, and this is because 4 is equal to 6 times something plus 4. It's just going to be 6 times 0 plus 4. But 4 is not an element of B, because if it were, then 4 would have to be, you'd have to be able to write 4 so that it's of this form here, 18b minus 2. 18b minus 2. And this would have to work for some integer b. Well, if you go and you solve for your integer b, you get something that's not an integer. So you can write which is not an integer. Or if you want to condense this line, instead of putting this here, you could say, you have the 1/3 and say that it's not an element of the set of integers. That would be fine too. And then we're done. So put a little box there. So I showed I have an element in set A. We know it's in set A because it fits the form, the definition for an element to be in set A, but it does not fit the form of an element that's in set B. Method of exhaustion. The method of exhaustion can be used for some proofs involving sets. And this is a method we've seen a couple times now. We first saw it in chapter 3. So we're going to use it here for example 2. So we're going to let set A be the set of elements 1, 2, 3, 4, 5, and 6. Set B is a set containing the elements 1, 4, and 6. We're going to use the method of exhaustion to prove that B is a subset of A intersection B. Now, if you think about this was like a Venn diagram, A intersection B is right here. And we're trying to prove that B is a subset of this intersection. This would mean visually, if you're thinking of this as a Venn diagram, I should have U here for universal set. This would actually have to look like this. For this to be true, it would have to look like this. Here's A. There's B. It's not a universal statement, it's not always true, but it's supposed to be true for these particular sets. And that's why we're going to use the method of exhaustion. So I'm going to say proof, and this is by method of exhaustion. And I'm going to leave like a note here to prove that B is a subset of A intersection B. We must show that every element in B is also an element in A intersection B. Okay. B here is equal to the set containing 1, 4, and 6. And then what's in their intersection? What was A again? A is the integers 1 to 6. 1, 2, 3, 4, 5, and 6. And we're intersecting that with set B, 1, 4, 6. And so in their intersection, you get 1, 4, and 6. So now you're going to go through each of these, and you're just going to show that it is an intersection. So the element 1 is in B, and 1 is in A intersection B. The element 4 is in B, and 4 is also in their intersection with A and B. And then the element 6 in set B is in set B, and 6 is also in the intersection. Thus, all the elements in B are also in A intersection B. By method of exhaustion, B is a subset of A intersection B. And then we'll end with a little QED. So that's your method of exhaustion when you have sets that are defined. And then proof by contradiction. We haven't actually seen anything like this yet, but we could do a proof by contradiction for some proofs involving sets. So we're going to see how that would play out in example 3. So I'm going to prove that the empty set is a subset of every set using proof by contradiction. So you write out proof. I'll put down by contradiction. And I'm going to suppose not. So I'm going to suppose that the empty set is not a subset of every set. That's what I'm supposing. I'm going to suppose not. So I'm going to suppose then that there exists, so suppose there exists a set, we'll just call it E, with no elements in it, and E for empty set, and a set, call it A, such that E is not a subset of A. So I'm going to suppose we have an empty set, and that is not a subset of some other set A here. By definition of this here, not a subset, there must be an element in E that is not an element in A. Remember, if you have, just go back for a second, if A is not a subset of B, then A has to have some element in it that's not in B. So if the set E, which is an empty set, is not a subset of A, then it has to have some element in it that's not in A. However, there can be no such element since E has no elements. That was mentioned up earlier in the proof. Suppose there exists a set E with no element in it. This is a contradiction. That's how the contradiction plays out. QED. So since you got a contradiction, since we were supposing that the empty set is not a subset of every set, and then we show that that couldn't happen because it led to a contradiction, then this is how we prove that the empty set, yes, it is a subset of every set. And then we're done with this section on 411, just some other different types of proofs that involve sets. You can try the homework, and then we are done with chapter 4.